Hello everyone, and welcome. Today, we're diving into an important topic, VRV versus package unit power calculation. We'll explore the differences in electrical load and breaker sizing between these two systems. This presentation will help you understand how to properly assess and size electrical components for each system type. So, let's get started and gain some valuable insights together. Let's take a closer look at the system comparison here. On one side, we have the package unit, which uses constant speed compressors. These compressors tend to draw a high starting current, known as LRA, which can put stress on the electrical system. Now, in contrast, the VRV system employs inverter-driven compressors. These are quite clever because they adjust their load dynamically, allowing for a soft start and significantly lower starting current. This difference is quite important because, as we see, VRV systems not only save energy, but also reduce the size requirements for breakers. This means more efficient operation and potentially lower installation costs. Overall, understanding these distinctions helps us choose the right system for efficiency, longevity, and cost-effectiveness, key themes as we aim to optimize our HVAC solutions. Let's take a closer look at rated capacity versus rated power. When we talk about cooling capacity, we're referring to the thermal performance, which is typically measured in kilowatts or BTU per hour. This tells us how effectively the system can remove heat from a space. On the other hand, rated or input power is about the electrical demand, the amount of power the equipment needs to operate. This is usually expressed in kilowatts as well. It's important to remember that when we're sizing electrical components like cables and breakers, we need to base our calculations on the input power or the rated current, not the cooling capacity. Why? Because the electrical demand determines the size of the wiring and breakers needed to ensure safety and compliance. So the key takeaway here is, always size your breakers from the input power or the rated current, not just the cooling capacity. This approach helps prevent electrical issues and ensures the system operates reliably and safely within its electrical limits. This connection between thermal performance and electrical demand is fundamental to designing efficient and safe HVAC systems. Let's take a closer look at this example from a manufacturer label. Here, we see the model number AM180AXVFNHS, which refers to a VRV outdoor unit. One key point to note is the cooling capacity, which is 50.5 kilowatts in thermal terms. This tells us how much heat the unit can remove from a space. Next, the rated power input is 12.7 kilowatts, meaning that's the amount of electrical power the unit consumes during operation. The rated current is 19.7 amperes, which is the current the unit draws at its rated conditions. Now, for proper electrical protection, we need to select the correct breaker. In this case, about 32 amperes with a C-curve characteristic is appropriate. It's important to choose the right breaker size to ensure safety and proper functioning. Speaking of incorrect methods, I want to highlight a common mistake. If someone simply divides the cooling capacity, 50 kilowatts, by the supply voltage of 400 volts, they might think an 81 amp breaker is needed. But that's incorrect because it doesn't account for the actual power input and the specific electrical characteristics of the device. This miscalculation can lead to selecting an overly large breaker, which isn't safe or optimal. So, the main takeaway here is understanding how to interpret these labels properly to select the right protective devices, ensuring both safety and efficiency in our systems. Let's walk through the step-by-step load calculation. First, to find the current I, we divide the power P by the product of the square root of 3, the voltage V, and the power factor PF. So, in this case, I equals 12.7 kilowatts divided by 1.732 times 400 volts times 0.9. When you do the math, that gives us approximately 20.4 amps. Next, we determine the minimum cable area, or MCA, by multiplying that current I by 1.25 to incorporate a safety margin. That results in about 25.5 amps, which means we should select a cable with a cross-sectional area of at least 4 times 6 millimeters squared. Finally, for the breaker, we choose a 32 amp breaker with a C-curve. This ensures the breaker can handle the starting currents typical for motors or other inductive loads without nuisance tripping. Overall, this process helps us ensure the wiring and protective devices are correctly rated for the load, maintaining both safety and efficiency in the system. All right, let's look at some common mistakes to watch out for. First, using cooling kW instead of input kW. This is a frequent error because people sometimes focus on the cooling capacity. But what really matters for sizing and energy calculations is the input power. Next, ignoring the manufacturer's MOP or MCA ratings. These are crucial because they tell us the maximum operating pressure and current ratings, ensuring we stay within safe and efficient limits. Overlooking them can lead to equipment failure or safety issues. Third, oversizing breakers is a mistake that can seem harmless, but actually leads to unnecessary costs. Larger breakers might cost more and can cause issues with coordinating protective devices properly. It's important to select the right size based on actual load requirements. And finally, not considering the soft start behavior of inverter VRVs. Soft start features are designed to reduce inrush current, but if you ignore this, you might underestimate the initial electrical stress on the system or misjudge the starting load. Recognizing this helps ensure a smoother and more reliable operation. Overall, being aware of these pitfalls helps us design more efficient, safe, and cost-effective systems, keeping everything aligned with best practices. All right, let's walk through the retrofit guide for the package to VRV connection. First, it's important to use the rated input power or the rated current listed on the equipment label. This ensures we're selecting the right electrical components and maintaining safe operation. Next, each VRV outdoor unit should have its own independent feed. This helps isolate faults and makes troubleshooting easier. When selecting the breaker, always refer to the manufacturer's MOP, or maximum overcurrent protection, to ensure proper protection without tripping unnecessarily. Additionally, you'll want to update the panel load schedule and the distribution board sheet accordingly. This keeps your documentation current and accurate. Lastly, it's crucial to verify that the voltage drop on the feeder is less than 3%. This is key to ensuring efficient operation and avoiding issues related to voltage loss. Overall, these steps help us create a reliable, safe, and efficient electrical connection for the VRV system, aligning with our goal of a seamless retrofit process.